Hi. In this set of lectures, we're going to talk about a particular model known as Replicator Dynamics. Now, Replicator Dynamics are interesting because they are used in three very different disciplines. They're used in psychology to model learning, they're used in economics to model populations of people learning, and they're used in ecology to model evolution. So when you think about Replicator Dynamics, here's the basic idea. You imagine there's some set of types out there. So there's some set of types that we can list from 1 to n. Now each type has a payoff, which is sort of how well that type is doing. And then there's a proportion of each type. So when you think of it, there's a population out there of types, and those populations are succeeding at different levels. Some are doing well, some are doing less well. And what we want to think of is we want to think of sort of the evolution or the dynamics of that process in terms of how the distribution across types change. Because what's going to happen? Think about it. If you've got a distribution of types and some are doing better and some are doing worse, the worst types should start copying the better types because the better types are doing better. So that's the process that Replicator Dynamics are going to help us try to understand. So if you think about learning, you can imagine there's a whole population of people out there, and they're trying different strategies. So some people are using strategy 1, some are using strategy 2, some are using strategy 3. So there's different proportions of people using these different strategies. When you look out there, you see those proportions. So you maybe see 40% are using strategy 1, 40% are using strategy 2, and only 20% are using strategy 3. So that might lead you to believe that, boy, strategy 1 and 2 are better. But then you can also maybe look at the payoffs of these. And maybe the people using strategy 1 are getting a payoff of 5, strategy 2 are using a payoff of 4, and strategy 3, maybe there's a payoff of 6. So now when you think about, well, what strategy should I use? It depends. If you're thinking in terms of which other strategies are more common, which we thought of in our sort of like standing ovation models and our contagion models and our conformity models, you might think, well, I'm going to do strategy 1 and strategy 2 because that's what other people are doing. But if you think in terms of a rational actor in terms of payoff, you'd say, well, I'm going to use strategy 3 because, look, that's got the highest payoff. So what Replicator Dynamics are going to do is they're going to allow us to model situations where both of those dynamics are in play, where people are both sort of copying more prominent strategies, and they're also copying strategies that tend to do better in the real world. Now, that's a model of learning, but we can use that same model, the same Replicator Dynamics model, to think about evolution. So now instead of strategies, you can think of there being phenotypes. So now there's phenotype 1, phenotype 2, phenotype 3. What do I mean by phenotype? So these could be, let's suppose these are frogs, and these frogs have different lengths of tongues. So this 1, 2, and 3 is just giving us different lengths. So maybe P1 is the phenotype is the longest tongue. And we could look at the proportions and say 50% are this type, 30% are this type, and 20% are that type. So you could look around and say this is the distribution of types. Now if you think about reproduction of this species, the more there is of a type, the more likely that it'll reproduce. So type 1s would be more likely to reproduce. But suppose we throw fitness in here and we say type 1s have a fitness of 5, type 2s have a fitness of 4, and type 3s have a fitness of 6. Now again you'd say, well, type 1s have an advantage because there's more of them, but type 3s have an advantage because they have higher fitness. So evolution is playing the same sort of trade-off. Things that exist in higher proportion are more likely to get reproduced just because there's more of them. But it's also the case that things that are more fit are a lot more likely to reproduce because, well, they're more fit. So what Replicator Dynamics allows us to do is model both learning and evolution using the exact same model and to look at the dynamics over a population. So again, the way to think of it is there's this distribution across these types, and that distribution is changing in response to the payoffs that those different types get in the case of learning, or to the fitness that those types get in the case of evolution. Now once we've studied Replicator Dynamics, we're going to go to a really interesting theorem called Fisher's fundamental theorem. Fisher's fundamental theorem talks about how the rate of adaptation of a population, so we can think of that population as adapting to its surroundings, the rate of adaptation is actually proportional to the variation of that population, so in terms of the variation in the types. So we'll write a formal theorem that says that. Now after we do that, what we're going to see is that that sort of runs counter to something we learned much earlier in the course, which was 6 sigma. Remember 6 sigma that you want to reduce variation. So Fisher's fundamental theorem says more variation is great because it allows you to adapt faster. 6 sigma said no, more variation is worse because it means more errors. So what we'll do is we'll try and make sense of that apparent contradiction in the final lecture in this sequence. All right, let's get started.